All right, welcome to this explainer. Today, we're going to completely demystify a groundbreaking solution to a problem you've probably run into, the frustratingly jerky nature of AI-generated videos. Listen, if you've ever watched an AI transformation sequence and felt like it was visually uneven or just kind of jarring, you definitely aren't alone. Today, we are digging into some seriously fascinating research that introduces a totally new way to measure and, more importantly, control the speed of meaning in video generation. So here's our roadmap for today's explainer. We'll start with the AI video pacing problem, then measuring meaning over time. After that, fixing pacing with ReTime. Then we'll look at retiming real cinematic video. And finally, we'll wrap up with the future of video control. Okay, kicking things off with section 1, the AI video pacing problem, and specifically why generative video can be so incredibly jerky. We're starting with a visual issue that literally undermines so much of AI video right now. Have you ever noticed how an AI-generated morph might sit there doing absolutely nothing for like 3 seconds, and then boom, it just suddenly morphs into a completely different object in a single frame? This is a huge common problem. Generative models are increasingly outputting sequences that are supposed to show gradual transformations, like morphs or object evolution. But they tend to change in meaning really unevenly. You get these long, drawn-out stretches with almost no variation, followed by abrupt, whiplash-inducing jumps where the transformation suddenly decides to catch up. And honestly, the visual we have up here perfectly captures this exact headache. Just look at the top row. Check out how that bead suddenly snaps into being a B. It's totally jarring, right? It completely ruins the perceptual coherence of the transition. It almost feels like a glitch. But now, look at the bottom row. That is the result of the method we are exploring today, which regenerates the video to force a smooth, evenly paced transition. Pretty amazing, right? But to fix the problem you see on the top row, we first have to figure out how to mathematically measure it. Moving right along to section 2, measuring meaning over time, with something called the Semantic Progress Function. So to actually fix this invisible villain of uneven pacing, researchers had to invent a completely new metric. Think of this Semantic Progress Function, or SPF for short, as basically a progress bar, but for meaning. It measures the cumulative semantic shift rather than just looking at changing pixels. The researchers compute the semantic distances between each frame, and then they fit a smooth curve that best reflects their ordering and meaning. So if that curve starts to deviate from a straight line, it directly reveals uneven semantic pacing. It pinpoints exactly where and by exactly how much a sequence is going off the rails. Now check out this graph. What's really fascinating here is that steep vertical line on the top right. It perfectly maps that instantaneous jarring jump from a cat to a lion you see in the top row. The cat transforms abruptly and boom, you see that orange arrow on the graph? That indicates an incredibly sharp increase in the rate of change. It's quite literally a mathematical reflection of visual whiplash. The bottom graph, on the other hand, shows the SBF after retiming. You can see how the semantic progression has been beautifully smoothed out into a steady, reliable climb. Here is the really crucial takeaway, though. If you just measure the raw pixel difference, actually think of it like doing a basic pixel-by-pixel comparison. It totally fails to identify these massive conceptual jumps. And that is exactly why the researchers use a model called SIGGRAPH to measure the actual semantic distance, or the real meaning between frames. SIGGRAPH translates the images into a conceptual map where measuring their similarity actually captures their underlying meaning. In fact, it's so precise, the researchers noted that SIGGRAPH's fine-grained sensitivity could even detect the exact onset of a subject's facial expression changing from calm to angry. It's that good. All right, section 3, fixing pacing with ReTime, or how we actually smooth out these jumps. Because diagnosing the problem is really only half the battle, right? Now we actually have to correct it. And that's where the ReTime mechanism comes in. It boils down to 3 really elegant steps: diagnosing the jump, stretching or squishing the time to compensate, and then regenerating the video so the whole transformation unfolds smoothly. And honestly, here is the absolute best part. This requires zero model fine-tuning. None. It's applied right at inference time. By warping the temporal positions, which basically means allocating way more time to semantically dense regions and compressing the stable ones, it forces the AI to pace itself. Now there is a catch. If you just warp all the timing equally, you end up making the video all jittery. So to avoid destabilizing the generation, they use what's called frequency-aware warping. This ensures the overarching transition paces smoothly without making the tiny local movements freak out. They apply stronger warping to the low-frequency bands, the ones that dictate the global structure of the video, while letting the high-frequency bands that handle short-range dynamics stay closer to linear time. It's an incredibly clever balancing act. And right here is where you really see the payoff. Look at the strawberry turning into a bird. If you rely on standard linear interpolation, like on the second row, you get this weird, ghostly, overlapping mess in the middle. But that bottom ReTime row, it allocates time perfectly for a flawless transformation. Because ReTime operates directly on the underlying model's feature representation, it maintains pristine visual fidelity while completely fixing the pacing. You can actually see the math working its magic right here on this graph. Look at the bottom right. That previously warped, messy timeline of the robot holding a balloon, it gets smoothed out into this beautifully steady, constant curve. The top row shows a stagnant start that just suddenly rushes to a sunset out of nowhere. But the bottom row shows the ReTime technique in action, stretching that sunset out evenly across all the frames. The visual transformation beautifully matches that straightened out line on the graph. Which brings us to section 4, retiming real cinematic video, because we are going way beyond just AI generation here. Yeah, you heard that right. This tech isn't just for AI output. You can actually use it to retroactively fix pacing in existing, real-world Hollywood footage. Look at this wild transition from the show Stranger Things. The original sequence on the top row kind of hides the metamorphosis behind an abrupt lightning flash. But the bottom ReTime row redistributes that semantic change to reveal incredibly smooth intermediate stages. The monster's original transformation relies on a harsh lighten cue to obscure the jump in logic. But by applying this method, the video is forced to reveal the gradual growth of the background elements, giving us a steady, step-by-step transition from human to monster. So how do they pull this off on regular video? Well, the algorithm basically carves up the timeline into contiguous, linear chunks. It isolates regions of constant meaning and then regenerates the intermediate clips between them. Think of it like mathematically carving up the semantic progress function into chunks where the semantic velocity is relatively steady. The end of each segment serves as the start of the next one, ensuring full coverage without any gaps. It essentially treats the boundaries as semantic keyframes and regenerates the content between them proportionally to the sheer magnitude of the semantic shift. I really want to highlight this quote because it is absolutely vital. It proves just how versatile this framework really is. You literally do not need access to the original underlying source code to perfectly repaste a video clip. Whether you're dealing with a closed-source AI model, a real-world camera capture, or heavily edited footage, you can still map its meaning and stretch or compress its timeline to be perfectly conceptually smooth. It's a game changer. And finally, Section 5, the future of video control, and what this all actually means for you. Let's talk about the massive implications this holds for digital creators. We aren't just limited to a flat, constant speed anymore. You can actually retime footage to match rising or falling exponential curves, intentionally accelerating or decelerating the visual story. Imagine you're a director, and you want the visual meaning of a scene to start off agonizingly slow, and then violently accelerate right at the end. Well, because the semantic progress function gives us the map, we can warp the territory to follow literally any mathematical curve we draw. And this synthetic test brilliantly validates just how accurate the underlying model is. We're looking at a rotating 3D cow on a blank background. The solid lines you see are the known angular velocity of the spinning cow, and the dotted lines are the semantic progress function tracking it. As you can see, the SPF perfectly maps onto constant, accelerating, and decelerating profiles purely by measuring the semantic change in the frames. So we finally have the ultimate progress bar for visual meaning. The only limitation left, honestly, it's just our own imagination. By untangling how fast a video changes from what is actually changing in the video, we are stepping into an era of unprecedented visual control. No more jerky AI generations, no more messy interpolations, just pure intentional storytelling. So I'll leave you with this. If you could take any existing footage and completely rewrite the speed of its meaning, what would you create next? Think about that, and thanks for joining me for this explainer.